Welcome to Ethiopedia. I am the Superchat. In this first video lecture, I present to you linear programming, specifically model formulation and computation. Contents we are going to cover in this section includes definition of terms, meaning new terminologies associated with linear programming, criteria for a problem to be considered as linear programming problem. Not all problems qualified to be considered as linear programming problem. So what are the basic criteria used for identifying linear programming problem? We will have a look on this. The third content, application of linear programming problem. The fourth content, linear programming problem model formulation. And the fifth content, graphic method of solving linear programming problems. For better exposition of the subject matter, let's start with examples, which we will refer back in every steps of discussion. That's in defining terms, in discussing criteria, in addressing applications, in formulating linear programming problem models, and in solving linear programming problem by using graphic method. This is the example. A chocolate manufacturing company produced two types of chocolates, type A and type B, by using three input materials, chocolate liquor, cocoa butter, and sugar. Each type A requires 8 units of chocolate liquor, 5 units of cocoa butter, and 4 units of sugar. And each type B requires 5 units of chocolate liquor, 2 units of cocoa butter, and 5 units of sugar. The company makes a profit of $4 per unit type A sold and $3 per unit type B sold. If the company has a total of 80 units of chocolate liquor, 40 units of cocoa butter, and 50 units of sugar, then what is the optimal product mix that maximizes profit? Second question, how much is the slack associated with the constraint? In this example, we have new terminologies like optimal product mix and slack. To address this and others, let's proceed to definition of terms. The first term that needs to be defined is the title of the subject we are gonna discuss, that is linear programming. Linear programming is a method of achieving best outcome, that is maximum or minimum of the objective function in a mathematical model whose requirements are represented by linear relationship. This definition is built from three pillars which themselves need to be defined. These are objective function, mathematical model, and linear relationship. Objective function is a function that defines some quantity that should be minimized or maximized. As we know, every organization has an objective that strives for its maximization or minimization. For example, the objective of manufacturing company is either to maximize profit, as the case in our example, or to maximize return on investment, or to maximize share equity, or to minimize operational costs. The objective of NGOs working in human rights protection is to fight individual violations of human rights. In linear programming problems, objective function is a linear function of decision variables. Again here, decision variable and linear relationship are new terminologies that need to be clarified contextually. Decision variables are unknowns that are expected to be estimated as an output of linear programming problem solution. In our example, the unknown is the optimal product mix. Optimal product mix means the product mix that gives a maximum of the objective function. In chocolate manufacturing company, the profit maximization function can be expressed in terms of the product mix of type A and type B chocolate as maximum profit is equal to 4x1 plus 3x2, where x1 is the amount of type A chocolate and x2 is the amount of type B chocolate. 4. The coefficient of x1 is the amount of profit generated by a unit type A sold. And 3. The coefficient of x2 is the amount of profit generated by unit type B sold. The total profit of the company is the sum of the profit generated by type A and type B chocolates. The other new terminology in linear programming problem definition is mathematical model. A mathematical model is an abstract model that uses mathematical language to describe the behavior of the system. Mathematical model is formulated by using a process of modeling or model formulation. So what does model formulation mean? Model formulation is a process of translating verbal statements of a problem into mathematical statement. Mathematical statement is a sentence which contains words and symbols. Here are the 4 steps for formulating a problem or formulating mathematical problem or model formulation. The first step is understanding the problem. Second step, describing the objective and each constraint. Third, defining the decision variables. And fourth, writing the objective and constraint in terms of decision variables. Here, the term constraint is new, which again needs to be defined. Linear constraint is an inequality that defines how the values of the variables in a problem are limited. It is a mathematical expression where linear terms, that is, coefficient multiplied by the decision variable, are added or subtracted, and the resulting expression is forced to be greater than or equal to, less than or equal to the right-hand-sided value. In chocolate manufacturing company example, each type A and type B chocolate uses 8 units and 5 units of chocolate liquor respectively. Since the available chocolate liquor is limited to 80 units, the mathematical expression of linear constraint can be written as 8x1 plus 5x2 less than or equal to 80, where x1 represents type A chocolate and x2 represents type B chocolate. The mathematical expression is the sum of the consumption multiplied by the respective chocolate type. So far, we have defined the important terminologies except linear relationship, which we will be clarified it under the requirements for using linear programming technique. So let's proceed to requirement for using linear programming technique. As we said earlier, not all problems can be considered as linear programming problem. So what are the requirements used to identify linear programming problems? The first requirement, all the quantifiable relationship in a problem have to be linear. Quantifiable means a relationship that can be expressed or measured as a quantity. So the other thing here is linear. What does linear relationship means? Which is the term we encountered in the previous definitions, that's from linear programming through linear constraints. The first requirement for a relationship to be considered as linear relationship is that all the variables in the equation has to be first degree. For example, f of x1, x2 is equal to 4x1 plus 3x2. This is the objective function of a chocolate manufacturing company, where the degree of both x1 and x2 is 1. So this relationship is linear relationship or a first degree relationship. The second requirement is proportionality. A change in variable results proportional change in that variable's contribution. If, for example, a manufacturing company make a discount after certain volume, proportionality is not satisfied and the model is no longer linear. For example, if a unit profit from type A chocolate is decreased from $4 to $3 after 1,000 pieces, its profit contribution decreased from 4x1 to 3x1, which is not proportional and the model is no longer linear. The third requirement for a relationship to be considered as linear relationship is additivity. The functional value is the sum of a contribution of each terms. In our example, f of x1, x2 is equal to 4x1 plus 3x2. Each decision variable, that is x1 and x2, should be multiplied with a constant but not with each other. If, however, the two products compete for market share in such a way that an increase in sales of one adversely affects the other, say if the increase in sales of X1 adversely affects the sales or profit of X2, then the additivity property is not satisfied and the model is no longer linear. The fourth requirement for a relationship to be considered as linear relationship is divisibility. The decision variable can be divided into non-negative integer, taking the fifth and the last requirement for a relationship to be considered as a linear relationship is that all objective function and constraint coefficients must be known constants, although it's not true in real life scenario. In real life context, it's impractical to determine exact unit profit and unit consumptions because of weight variation of inputs and outputs within the permissible deviation and the difficulty in assigning unit costs associated with overheads. In general, a relationship that fulfills all the above 5 requirements is considered as linear relationship. Also, it fulfills the first requirement for the problem to be considered as linear programming problem. The second requirement for using linear programming technique is that the values of the variable has to be constrained in some way. For example, in our example, the chocolate manufacturing company is constrained or limited by the availability of inputs. A third requirement for using linear programming technique is that the goal has to be to find values of variable that will maximize or minimize some quantity. In the chocolate manufacturing company, profit maximization is the goal of the company. The fourth requirement for using linear programming technique is that each decision variable in any linear programming model must be non-negative, irrespective of whether the objective function is to maximize or minimize. It's impractical to produce negative products, hence x1 greater than or equal to 0 and x2 is greater than or equal to 0, where x1 is type A chocolate and x2 is type B chocolate in our example. Generally, our example fulfills all the 4 requirements for using linear programming technique and is considered as linear programming problem. Next, let's jump to applications of linear programming problem. Linear programming problems are mostly applicable in mathematics and engineering and industries like transportation, energy, livestock production, and manufacturing as well. In transportation, linear programming problem is used for determining the minimum transportation cost for goods transport across each available route subjected to supply, availability, and demand. As we discussed earlier, linear programming problems have objective function, decision variable, and constraints. So in this example, the objective function is cost minimization, decision variables are available routes, and the constraints are supply, availability, and demand. In energy industry, linear programming problem is used for determining minimum energy cost in manufacturing process subject to energy efficiency of the technology used and the suitability of energy generating process and the type of energy source. Here the objective function is again cost minimization. Decision variable is type of energy source. There are different types of energy source. Constraints are availability and energy efficiency of the source. In livestock production, linear programming problem is used for determining how much of each foodstuff of livestock diet to buy so that the total diet cost is minimized subject to constraints on minimum and maximum level of nutrients. Here the objective function is again minimizing diet cost. Decision variable are different foodstuffs and the constraint nutrient content of different foodstuffs. In manufacturing companies, linear programming problem can be used for determining a production plan where a firm chooses for the profit maximizing of production subject to resource, labor, or raw material constraints. Here the objective function is profit maximization. decision variables are production plans or the alternative production plans. The constraints are resources like labor and raw materials. Next, let us step to problem formulation or modeling. As we defined earlier, problem formulation or modeling means translating verbal statement into mathematical statement. The following are the steps for translating verbal statement into mathematical statement. Alongside explaining these steps, we will formulate mathematical model for the chocolate manufacturing company example. Step 1 is identifying the objective of the problem. In our example, the objective is profit maximization. The second step in model formulation is identifying decision variable and constraints. As we discussed, decision variables are unknowns that are going to be determined, and constraints are limitations in an attempt of achieving the objectives. The chocolate manufacturing company intent is to determine the amount of type A and type B chocolate that combinedly gives a maximum profit. So the decision variables are type A chocolate and type B chocolate. And also, the fulfillment of this company objective is subject to the availability of input materials, that's chocolate liquor, cocoa butter, and sugar. Hence, the constraints are chocolate liquor, cocoa butter, and sugar. The third step in model formulation is write the objective function in terms of decision variables. As it is given in the problem, the unit profit generated by type A chocolate is $4. So, the profit contribution of X1 amount of type A chocolate is 4X1, meaning a unit profit multiplied by the amount to be produced. Similarly, profit contribution of type B chocolate is 3X2 because a unit type B chocolate generates a profit of $3, then the unit profit generated by X2 amount is 3X2. Thus the objective function, which is the sum of the profit generated by each profit, is Z max is equal to 4X1 plus 3X2. The fourth step in model formulation is write the constraint in terms of decision variables. As it is clearly depicted in the problem, chocolate liquor usage of type A chocolate is 8X1, meaning quantity to be produced multiplied by a unit consumption. Chocolate liquor usage of type B chocolate is 5X2. Again, quantity to be produced multiplied by a unit type B consumption. The total chocolate liquor usage, which is the sum of the chocolate liquor used by type A and type B chocolate, is 8X1 plus 5X2. As we know, a total unit of chocolate liquor used is always less than or equal to the total chocolate liquor available. Thus, the chocolate liquor constraint inequality can be written as 8X1 plus 5X2 less than or equal to 80. The expression at the left represents the amount consumed, and the expression at the right side of the inequality represents the total chocolate liquor available. Similarly, the total units of cocoa butter used is less than or equal to the cocoa butter available. So 5X1 plus 2X2 less than or equal to 40. 5 is amount cocoa butter used by a unit type A chocolate, and 2 is the amount cocoa butter used by type B chocolate. Again, for sugar constraint, total units of sugar used is always less than or equal to the sugar available. 4X1 plus 5X2 less than or equal to 50. 4 is the amount used by a unit type A chocolate, and 5 is the amount used by a unit type B chocolate. The fifth step in model formulating is to add the non-negativity restrictions. The company can produce neither type A nor type B chocolate. Thus, X1 is always greater than or equal to 0, and X2 is always greater than or equal to 0, where X1 represents type A chocolate and X2 represents type B chocolate. The sixth step is to write the complete mathematical model. It's simply putting together all the equations and inequalities formulated from step 1 through step 5. So this is the complete mathematical model, z max is equal to 4x1 plus 3x2, which is the objective function, subject to chocolate liquor constraint, cocoa butter constraint, sugar constraint, and non-negativity restrictions. Having this, let's move on to graphic method of solving linear programming problems. Linear programming problem involving only two decision variables can be solved by using graphic solution procedure. The question that might raised here is that why only two decision variables? The reason is this. When the decision variables are only two, it is easy to put one variable on the y-axis and the other variable on the x-axis. But when the variables become more than two, it is impossible to portray them on a simple xy plane. Problems of such type, meaning problems having more than two decision variables, can be solved by using a simplex method, which we will discuss separately in the upcoming video lectures. Although two decision variable models are hardly exist in practice, the treatment provides concrete foundation for the development of general simplex algorithm, meaning although graphic method doesn't have much practical application because of its feasibility only for two decision variables, having a knowledge about the subject matter lay a favorable ground for the development of simplex algorithm. Graphic method include two steps. The first step, determination of feasible solution space or feasible region. The second step, determining the optimal solution from among all feasible points or in the solution space. The new terminology, feasible solution or feasible region and feasible points, will be discussed later after drawing the graph, as the graph helps to show the real picture of what this means. Drawing the graph usually starts with mathematical model, which we already formulated before. This is a mathematical model. Z max is equal to 4x1 plus 3x2, the objective function, which is subject to chocolate liquor constraint, cocoa butter constraint, secure constraint, and the non-negativity restrictions. In drawing the graph, what one should do is represent the decision variable in the vertical axis and the other decision variable in the horizontal axis, and then draw the graph of the constraints. In doing so, again one should consider the following. The first consideration is non-negativity of the decision variables. As we know, both x1 and x2 are greater than or equal to 0, meaning the variable to be represented in the y-axis, say x2 in our case, starts from 0 and extends upward, and similarly the graph of the horizontal axis starts from 0 and stretches to the right. Hence, the solution space area is restricted to first quadrant. As we know, xy plane has 4 quadrants. In quadrant 1, both x and y are positive. In quadrant 2, x is negative and y is positive. In quadrant 3, x and y are negative. In quadrant 4, x is positive and y is negative. In our example, both x1 and x2 are greater than or equal to 0, meaning they are positive. Thus the graph lies, or the solution space lies, in quadrant 1. Second, replace the inequality in constraints with equation and draw a straight line graph by locating any 2 points on it. The resulting equations of the constraint look like this. 8x1 plus 5x2 is equal to 80. 5x1 plus 2x2 is equal to 40. 4x1 plus 5x2 is equal to 50. Just what we do is substituting the sign less than or equal to by equality sign. So to draw the first constraint, that is the chocolate liquor constraint, locate any 2 points, usually the intercepts, at all points on the vertical axis. The value of x1 is 0. Substituting 0 to x1 in the chocolate liquor equation gives 0 times 8 plus 5x2 is equal to 80, meaning x2 is equal to 80 over 5, which is equal to 16. So the first order pair is 0,16. Again, at all points in the horizontal axis, x2 is equal to 0. Substituting 0 to x2 in the equation gives 8x1 is equal to 80, meaning x1 is equal to 10. So the second order pair is 10,0. From this calculation, one can understand that using the intercepts is advantageous, since either of the two values is already known, that is 0. At x2, the value of x1 is 0, and at any point on x1, the value of x2 is 0. After finding these two order pairs, draw a straight line graph by joining the 2 points. This is the graph. All points computed as 8x1 plus 5x2 is equal to 80 lies on the line, on the solid line. The question is, to which side of the graph line does the point satisfying 8x1 plus 5x2 less than 80 lies? Is it above the line or below the line? To check which side satisfying the inequality, take any 2 points, say 0, 0, and compute for the result. If the resulted inequality is true, the feasible side lies on this side where the chosen point is located, otherwise on the opposite side. To compute the result at 0, 0, 8 times 0 plus 5 times 0 less than 80, meaning 0 less than 80, which is true. Thus, the point satisfying 8x1 plus 5x2 less than 80 lies below the line. That is, the side shaded with the orange color, or the side bounded at the left by the graph of S2, at the bottom by the graph of x1, and at the top by the graph of 8x1 plus 5x2 is equal to 80. To draw the graph of the chocolate liquor constraint on the same XY plane, locate any 2 points, usually x-intercept and y-intercept. In this case, y-intercept is 0,20 and x-intercept is 0. Then draw a straight line graph by joining the 2 points. This is the graph. Shade the side feasible to both constraints. That's 8x1 plus 2x2 less than 40, the cocoa butter constraint, and 8x1 plus 5x2 less than 80. Again here, the feasible region lies below the line, and the area shaded with darker orange is a region satisfying both inequalities. At the unshaded part, 5x1 plus 2x2 less than 40 is true, but 8x1 plus 5x2 less than 80 is false. On the other hand, at the region shaded with orange color, 8x1 plus 5x2 less than 80 is true, but 5x1 plus 2x2 less than 40 is false. Our focus is on the area satisfying both inequalities, thus the area shaded with dark orange color is the feasible space. To draw the graph of 4x1 plus 5x2 is equal to 50 in the same xy plane, first locate the intercepts. As usual, y-intercept is 0,10 and x-intercept is 12.5, 0. Draw a straight line by joining the 2 points. This is the straight line. Shade the side feasible to all the 3 constraints. What are these 3 constraints? 5x1 plus 2x2 less than 40, 8x1 plus 5x2 less than 80, and 4x1 plus 5x2 less than 50. The region shaded with blue color satisfies all the 3 constraints. This region is called feasible region or feasible solution space. Now the question is, what is feasible region? Feasible region is simply a region containing all the feasible solution points. Feasible solution points are again any solution point on the boundary of the feasible region or within the feasible region. These solution points that satisfy all the constraints or combined constraints. In this graph, the feasible region is bounded at the left by the graph of x2 at the bottom by the graph of x1, at the right by the graph of 5x1 plus 2x2 is equal to 40, and at the top by the graph of 4x1 plus 5x2 is equal to 50. The solution point on either of the shaded portions of this graph and in between them are called feasible solution points. The graph of 8x1 plus 5x2 is equal to 80 has no contact with the shaded area, rather it is located above or farther from the origin. This practically means that the chocolate liquor constraint didn't affect the feasible region. That is, the feasible region would be the same whether the chocolate liquor constraint was included or not, which tells us that enough chocolate liquor is available to accommodate additional production level of type A and type B chocolates. Once the feasible region is identified, it is important to compute the intersection between one constraint with the other constraint, one decision variable with the other decision variable, or constraint with decision variable in the area which are in contact with the feasible region, because it is at either of these points the optimal solution lies. So to compute the intersection between decision variables, which we assigned as O is the origin, 0, 0. The intersection between x2 and 4x1 plus 5x2 is equal to 50, which we assigned A is 0, 10. To compute this point, just substitute 0 in place of x1 in the equation 4x1 plus 5x2 is equal to 50, because x1 is 0 at all points in x2, so 0 plus 5x2 is equal to 50, meaning x2 is equal to 10. To find the intersections of 5x1 plus 2x2 is equal to 40 and 4x1 plus 5x2 is equal to 50, which we assigned point B, choose either of the two variables, then multiply equation y by the coefficients of chosen variable in equation 2 and equation 2 by the coefficient of chosen variable in equation 1. For our case, let's choose x2 and then multiply equation 1 by 5, which is the coefficient of x2 in equation 2, and equation 2 by 2, which is the coefficient of x2 in equation 1. For the first equation, we will find 25x1 plus 10x2 is equal to 200. For the second equation, 8x1 plus 10x2 is equal to 100. The intention was to make the coefficient of the chosen variable similar in both equations and then subtract each other to 0 in order to solve for the other variable, that is x1. Now we make the coefficient of x2 similar, that is 10, then subtract equation 4 from equation 3. We will find 70x1 plus 0x2 is equal to 100, meaning x1 is equal to 100 over 17. Substituting the value of x1, that is 100 over 17, to either of equation 1 or equation 2, we will find x2 is equal to 90 over 17. The 4 points, that is the intersection between 5x1 plus 2x2 is equal to 40 and x2, which we assigned C is 8, 0. Again, to solve this, substitute 0 to x2 in the equation, then solve for the x1, because x2 is 0 at all point on x1. Here are the 4 points of intersection, which are called extreme points. Extreme points are vertices of the feasible region. Why is it important to determine these extreme points or vertices of the feasible region? Because the optimal solution to linear programming problem can be found at an extreme point of the feasible region. So, to find the optimal solution, just take the objective function and compute its value at each extreme points, at the 4 extreme points. The objective function is zmax x1, x2 is equal to 4x1 plus 3x2, which was determined earlier. To compute for point A, zmax at 0, 10 is equal to 4 times 0 plus 3, 10. 3 times 10 is equal to 30. To solve for point B, Z max at 100 over 17, 90 over 17, which is equal to 4 times 100 over 17 plus 3 times 90 over 17, which is equal to 39.41. Again at point C, Z max 8, 0 is equal to 4 times 8 plus 3 times 0, which is equal to 32. And for the origin, Z max at 0, 0 is equal to 0. Meaning, if the company doesn't make any of the two products, no doubt its profit will be 0. Therefore, the optimal product mix is 100 over 17 units of type A chocolate and 90 over 17 units of type B chocolate, because the maximum profit of $39.41 is attained only when the company produced the mentioned quantity of each products. After determining the optimal products means, it is simple to calculate slack variables, but before calculating the slack variable, let's define what it means. Slack variable is any unused input material associated with the constraints. So, for calculating a slack variable or the amount of unused materials, it's important to determine the amount used by substituting optimal solution value into the constraint equations. As we figure out in the step of writing constraint in terms of decision variables, amount used is always less than or equal to amount available, meaning 8x1 plus 5x2 less than or equal to 80. This is the chocolate liquor constraint. 5x1 plus 2x2 less than or equal to 40. This is the cocoa butter constraint. 4x1 plus 5x2 less than or equal to 50. This is the sugar constraint. The expressions at the left side of the inequality represent amount used. To determine amount used, just substitute optimal products means, that is 100 over 17 units of type A and 90 over 17 units of type B to the respective expressions and solve for the amount. Therefore, chocolate liquor use is equal to 8 times 100 over 17 plus 5 times 90 over 70, which is equal to 73.53. Cocoa butter used is equal to 5 times 100 over 17 plus 2 times 90 over 17, which is equal to 40. Sugar used is equal to 4 times 100 over 17 plus 5 times 90 over 17, which is equal to 50. Finally, calculate the slack variable by subtracting amount used from amount available. We can tabulate such calculation in the form like this. Input, chocolate liquor, cocoa butter, and sugar. Amount used, chocolate liquor used is 73.53 units, cocoa butter used 40 units, sugar used 50 units. Amount available, chocolate liquor available 80, cocoa butter available 40, and sugar available is 50. The slack, that is the difference between amount available and amount used. The chocolate liquor slack is equal to 80 minus 73.53, which is equal to 6.47. Cocoa butter slack 40 minus 40, which is equal to 0. Sugar slack is equal to 50. Sugar slack 50 minus 50 is equal to 0. As one can clearly see from the graph, and the optimal solution is attained at the intersection of the sugar and cocoa butter constraint lines. But the chocolate liquor constraint line is located above this point. The graph and the calculation reveals that by producing 100 over 17 units of type A and 90 over 17 units of type B chocolate, the company consumed all sugar and cocoa butter inputs, but 6.47 units of chocolate liquor is left unused. These are the summaries of the steps we used in solving linear programming problem by using graphic method. In step 1, we formulate the mathematical model. In step 2, we construct the graph of decision variables and constraints. In step 3, we determine the valid side of each construct lines. In step 4, we determine feasible region and extreme points. In step 5, we compute optimal solutions and the slack variables. That's all for today. Thank you for listening. In the coming video, we will solve linear programming problems for maximization problem. And this is